Hi, welcome to this tutorial on building end-to-end data pipelines from the operational database to the BI tool using only open source tools. The only thing that you need is a Kubernetes cluster. No cloud data warehouse is required. In this video, we'll be using the Killercoda online environment, which gives us a testing Kubernetes cluster for free. So if you want to follow along, click on the link in the description. There's no need to install anything and you can run it all in the browser. In the tutorial, we're going to go through the whole process that a typical data engineering team has to go through to get the data that is continuously generated inside a company, clean it, transform it, and make it available to downstream users. The goal is to walk through every step so that you can go ahead, copy the tutorial code, and get started on your own data platform. But before we jump in, let's give you a quick overview of the process. Typically, data is going through several stages, from its raw form until it can be served as a useful asset. On the one side are the operational systems of a company that are continuously generating data. These can be transactional databases, event streaming platforms, or external APIs of marketing tools or payment providers. These systems are shown here on the left, under generation. In this tutorial, we'll be using a Postgres database as our operational system. The analysis of the data is performed in a separate analytical system. The purpose of the system is to store, clean, transform, and serve the data. It is shown here as the central block. On the other side, we have analysts, data scientists, and machine learning engineers who want to use reliable and ready-to-use datasets. These are shown here on the right. This tutorial focuses on the data engineering tasks related to the analytical system in the middle. One fundamental building block for the analytical system is the storage layer, as it underpins all other tasks. In modern cloud data platforms, the storage layer is realized as a data lakehouse, which can store structured and unstructured data. The first data engineering task is to ingest the operational data into the lakehouse. In this tutorial, the ingestion is performed using the Airbytes specification that allows to ingest data from over 200 different data sources. Once the raw data is loaded into the lakehouse, the next step is to transform the data into the desired form. We will use SQL queries to define iceberg materialized views for the transformation. And then we will use Dashtool to generate jobs that use the Apache Data Fusion query engine to periodically update the materialized views. The next step is to make the data available to downstream users. For that, we will use an Apache Arrow Flight server that allows efficient data transfer to consumers. To demonstrate one such consumer, we will use the BI tool Apache Superset to access the transformed data. Now that we know what we're trying to build, let's jump in and perform the actual steps. If you want to follow along, head to killercoda.com/dashbook and you will find the Dashtool Postgres example here. By clicking on the tile, it will load the tutorial environment. But first, we have to log in. You can use an identity provider like GitHub, GitLab, or Google. I'll be using my GitHub account. Let's wait until I'm signed in. The Killercoda environment is running a virtual machine in the background with a small Kubernetes cluster. It provides us with the tutorial text on the left and an editor and a console on the right. The editor and the console. Let's go ahead and hide the hidden files. I'll skip over the introduction because we already covered this in the video. Let's click on Start to start the tutorial. The tutorials are set up so that all steps can be performed by code cells. These code cells can be executed in the console by clicking on them. Let's demonstrate this by clicking on this code cell here, which will install the Argo workflow engine. We can see here on the right that it will install the Argo workflow engine in the background. Let's click on Next to install further requirements. As described in the introduction, we require several services for this tutorial. First, we need a Postgres database as our operational system. Then we need cloud storage for the lakehouse. And we need an Apache Superset server as our BI tool. All these services require credentials to access them. By executing the next code cell, we will create Kubernetes secrets that will hold these credentials for us. Keep in mind to use more secure passwords for production environments. Now that the secrets are set up, we can create the services in our cluster. We can do this by executing the next code cell here. To create the services, the cluster needs to fetch the according Docker images from the internet. This may take around 5 minutes. You can check if the pods are running by executing the next code cell here. We can see here at the status field that it's still creating the containers and still downloading the images. Let's wait until all the containers are running. I skipped ahead a couple of minutes, so let's run the command again to see if the pods are running. We can see here at the status field that now all pods are running. Normally, we would need to create a reverse proxy and an ingress resource to access our cluster from the public internet. To simplify this process, we will just use port forwarding, which we can start by executing the next code cell here. Let's start with the actual tutorial by clicking on the next cell. The task we would like to do is to ingest the operational data from a Postgres database into the lakehouse. This is also often called extract and load, or EL. In this tutorial, we'll be using the Airbyte specification to handle the extraction and loading for us. For that, we have to define a data source to extract the data from, and a destination to load the data into. We will use the Airbyte Postgres source to extract the data from our database. The great thing about the source is that it supports log-based replication, so that it will only extract new data and we don't have to worry about which data we've already extracted. To enable log-based replication, we have to execute the next code cell here. Additionally, we'll use the Iceberg destination to store the data in Iceberg tables in our lakehouse. Dashtool will help us set up the source and destination. The only thing we need to do is to create config files for the source and the destination. We can find the sample configuration files in the browser folder under the inventory directory named postgres.index.json. This contains the parameters for our Postgres source. Here we can see that first it specifies which Docker image to use and then defines parameters for our source and our destination. Under the source field, we can see connection parameters for our Postgres database and additional parameters. For example, which replication methods to use. Under the destination field, it contains parameters for our Iceberg tables. For example, the catalog URL for the Iceberg catalog to use. And additionally, connection parameters for our cloud storage. In this tutorial, we'll be using a local cloud storage in our Kubernetes cluster, but you can replace these parameters to use AWS S3, for example. Following the medallion architecture, we load the raw data into the browse stage, indicating that the data is not consumption ready yet. This is why we store the configuration files in the browse folder. Dashtool automatically integrates with Git version control. Before we can add the source and the destination, we have to create a new Git repository and create a main branch for it. We can do this by executing the next code cell here. In order for Dashtool to recognize the configuration file, they have to commit it to a Git branch. It's good practice to first create a new branch where you can verify that everything works as expected before you add the commits to the main branch. Iceberg tables support branching, so Dashtool will create the corresponding branch on every iceberg table. Let's add the configuration file to the bronze branch by executing the next cell here. Now Dashtool is able to recognize the configuration file. By running Dashtool build, Dashtool will create the corresponding iceberg tables in the lakehouse. These tables will not contain any data at the beginning. We must first run a workflow that ingests the data from our source system. So let's execute the Dashtool build command. Luckily, Dashtool can also help with running the workflows. Running Dashtool workflow will create an Argo workflow configuration that can be used for the ingestion. So let's execute the cell by clicking on it. We can have a look at the Argo workflow configuration file that has been created in the Argo folder. This configuration file contains templates for Docker images. For example, here's a Docker image for the Airbyte Postgres source. And Dashtool automatically adds the required secrets to the configuration file. We can execute the next code cell to apply this workflow configuration to our cluster so that we can run Argo to run our jobs. We will do the next step in the Argo Workflows user interface, which we can access by clicking on this link. So now we're accessing the Argo server that is running in our cluster. Let us first close these info windows. To see the workflow that we've created, head to the cron workflows tab on the left. We will need to remove the undefined filter here to see our workflow. Let's click on the workflow to find more information. Here we can see the schedule that the workflow is typically executed. We can also manually start the workflow by clicking on the Submit button here. So let's do this. Now the Argo workflow engine is executing the Argo workflow. This will also take some time. I skipped ahead until all jobs finished. Now the data from our source system should have been ingested into the lakehouse. Let's verify that the data has been ingested as expected. For that, we have to merge the bronze branch into the main branch, because we can only access data on the main branch. And we will run Dashtool build again to also merge the bronze branch of our iceberg tables into their main branch. So let's do that by executing it. To access the data from the lakehouse, we will use the BI tool Apache Superset that we've installed before. For that, we head to the Superset console, which we can reach with this link. The username is admin and the password is password. So let's log in. To access the data from the lakehouse, we first have to set up a new database connection. We can do this by going to the Settings panel and clicking on Database Connections. To register a new connection, we click on Database and choose Other as our connection. Then we can go back to the tutorial and copy the connection URL by just clicking on it and pasting it as the SQL Alchemy URI. Then we can test the connection and we see that the test succeeded. So let's connect to the database. To verify that the data has been injected correctly, we go to the SQL Lab tab. And let's copy our SQL string that we want to execute and paste it into this field right here. So let's select all from our orders table and run the query in Superset. As we can see here, the data has been ingested correctly from our source database. Now that we loaded the raw data into the lakehouse, it's time to transform the data into the form that we need. Let's continue with the tutorial and click on Next. In this tutorial, we will create the medallion architecture with a bronze, a silver, and a gold layer. As we've just seen, the bronze layer contains the replicated raw data from the operational system. The silver layer is for cleaned and properly modeled data to provide the basis for further analysis. The gold layer is for ready-to-use datasets for downstream consumers. Let's get started on the silver layer by creating a new silver Git branch. We can do this by executing the next code cell. The silver layer is a good place to apply dimensional modeling. I'll provide a link in the description that gives a quick introduction to dimensional modeling, and I won't go into too much detail here. The general idea is to distinguish between quantitative and qualitative data. The quantitative data captures measurements of a business process and is stored in so-called fact tables. The qualitative data provides context to the measurements and is stored in so-called dimension tables. To create new tables with Dashtool, we only need to define new SQL files that contain the select clauses for the table definitions. For that, let's have a look at how to define an orders tables, which is an example for a fact table. We can find it under the silver directory as fact order SQL. The table measures how the business process customer orders performs by recording the quantities of the products being sold. If you look at the attributes of the table, we see that it contains only quantitative information about an order event. There's no detailed information about the product or the customer that made the order. On the other hand, we have the product table here with the name dim product, which is an example for a dimension table. It provides extra context about entities in the business process. For example, the product name or description. In the silver layer, we want to clean the data, which means to rename columns, change their format, or drop certain columns. For Dashtool to take the silver folder into account, we need to commit its files to a branch. We can do this by executing the next code cell here. To apply the transformation, let's run the Dashtool build command that will create iceberg materialized views for every SQL file that we've created. Let's do that by executing the code cell. Similar to before, we need a workflow that regularly refreshes the data of the materialized views. We will create it by running the Dashtool workflow command. Again, we can have a look at the workflow definition. Now it also contains a container to refresh the iceberg materialized views. Here. We apply the new workflow by clicking the next code cell here. Let's head back to the Argo Workflows UI to schedule a new workflow run. We will go again to the cron Workflows tab, go on our workflow, and submit a new run. Again, we have to wait until all jobs are finished. I skipped ahead until all jobs finished. Now we can go back to the tutorial and merge the silver branch into the main branch. Let's run Dashtool build again to also apply this to the iceberg tables. Let's start our analysis with the next step of the tutorial. Now that we have clean and modeled data, we can start asking questions about our business. Let's create a gold branch to start an analysis. We could ask ourselves the question of How much do our monthly sold products weigh? To answer this question, we need information from our fact order and dim product tables. Let's have a look at the SQL file in the gold folder to see how this can be done. We can see that the query joins the two tables to calculate the total weight of the products per month. Just as before, we'll add the file to the gold branch for Dashtool to take it into account. And we run the Dashtool build command for our Dashtool to create the corresponding materialized views in the lakehouse. And just as before, we will create a configuration file with Dashtool workflow and apply the new configuration file to our cluster by executing the next code cell. Let's head to the Argo workflow console again to schedule a new workflow run. Similar to before, we go to the cron workflows tab, click our workflow and click on the submit button. Again, I skipped ahead until all jobs finished. To access the data, we have to go back and merge again the gold branch into the main branch. Let's run Dashtool build again to also merge the gold branch into the main branch of our iceberg tables. And just to be sure, create an updated workflow file and also apply the updated workflow file to the cluster, because now everything is on the main branch. To access the data, we can go to the superset console and query our table in the gold folder. Let's execute the query. As we can see, we get the results to our analysis. Now we can head to the next step of the tutorial. Let's click on the next button. The great thing about materialized views for the transformation is that they keep themselves up to date. Let's test this by inserting additional data into our operational database and check if the data in the lakehouse changes. We'll run the SQL command shown here by executing the code cell above. This will add additional entries into our operational database. So let's execute the script. Our workflow automatically runs every day. So we would need to just wait and the data should eventually be in the lakehouse. To speed up the process, we can start the workflow right away. So let's head to the Argo Workflows panels and start the workflow again. I waited until all jobs finished and the materialized views have been refreshed. To see if the data actually arrived in the lakehouse, let's head to the superset console. Here we can see the data from our previous query. Let's just execute the query again and see if the data changes. As we can see, the new data is readily available. Congratulations! You just built end-to-end data pipelines that automatically refresh themselves. Thanks for watching. I really hope you enjoyed the video and see you next time.